Good afternoon, everybody. Hope everybody is alert and paying attention after that, after lunch. So, welcome to my talk. Why can't my app open that file? A deep dive into the Android app sandbox. When it says deep dive, let me just be clear here that it's not going to be, it's not going to be that deep. We've only got 30 minutes, 40 minutes. So it's going to be kind of, past the knees probably, but not, hopefully, not over the head. That's my intention, at least. So I'm Chris Simmonds. I'm a consultant. I've been doing stuff with embedded systems for many, many years. I do a lot of work with embedded Linux, and also I do a lot of work with embedded Android, because as we know, Android is just Linux. It's the same thing. I've written a book on the subject, just saying. It's a book. You can go buy it if you wish. You can also see what I've been doing. So I have a blog looking after the inner penguin at tunet.co.uk. You can follow me on Mastodon. I don't do Twitter or X, whatever it is these days. And I'd be happy to link with you all on LinkedIn. So that's me. You can't avoid me. I'm definitely here. So this talk is really, I want to reveal to you some of the secrets of what goes on inside the platform. So specifically, we're going to be talking about the Android sandbox, what it is, how it works, whether it's a good thing or a bad thing. And I guess what I would like you to take away from this is some additional knowledge as to how all this stuff works. It's not just magic. There is some stuff behind it. And I'm going to finish off at the end by talking about how do you bypass the restrictions. So, which files can my app access? So I'm just talking about just regular apps, regular user-installed apps right now. So you can access the private files stored in internal storage, private files stored in external storage, and shared files in external storage. And that's basically it. So you, as in writing apps, you're very much firewalled as to what you can do. I should probably say sandboxed. Anything else you try and do, you're going to get a file not found exception or a security exception or something, but you definitely are not going to be able to read, write, or do anything with that file. Good or bad? Well, obviously it's good, otherwise we wouldn't be talking about it, I guess. It is essential that there is a firewalling around applications, because we install all kinds of apps onto our phones. We don't want app A stealing all the information from app B. So in my example, I want to be sure that if I have my banking app on my phone, that no other app can come along and steal my banking credentials and empty my bank or whatever. So obviously, we need that level of security. That's what it's all about. But it has some downsides, obviously. It makes it harder to share data between apps. I'm not really going to go into that in too much more detail, but it is a fact. And also, there's some useful stuff out there that I might want to be able to read in my app. So this isn't so much an issue if you're just doing regular things on smartphones and such like, but if you widen things out to beyond smartphones, or if you are the people implementing the smartphone, then this becomes a problem because you need to access all kinds of stuff. Peripherals, make LEDs turn on and off, all this kind of stuff. So being able to access low-level files can be useful. And I'll amplify that a little bit towards the end. So the main topic then is the sandbox. So this is one of the original design decisions of Android. So right from day one, when Android was released, way back in 2008, the sandbox was there. And it is fairly robust. It's a design that's kind of persisted all this time. So it was basically a good design. So the basic idea then is to isolate applications from each other and also from the operating system. So an app can't go and delve into and in some ways modify and corrupt the behavior of the operating system. And the sandbox is based on Linux, hence my Linux interest here. So I want to basically amplify that a little bit and show you how the various features actually work. And there are really two components to this. I'm going to be talking about memory isolation and file isolation. And these are both based on properties of the Linux kernel. So I need to give you a little bit of background, assuming you're not Linux people, which you might well be, in which case you can just switch off for a moment. So a Linux process. Linux process is an area of virtual memory, and the code for the process, the program, whatever it might be, is in that area, plus the data, the stack, the heap, whatever else. Every process has a process identifier, or PID, and that is allocated by the system when the process is created. Essentially, PIDs start from 1, and then they increment upwards every time a new process is created. A process contains one or more threads, and the threads have their own identifiers called thread identifiers, or TIDs. Crucially, a process is owned by an owner. So in typical Linux or Unix world, this would be the person who logged on. And that has an identifier called a UID. As well as the owner, we also have the concept of groups. So with group IDs, we can actually group a number of processes together. And we can do interesting things with that. And it turns out, as well as the base group ID, you also get some supplementary group IDs. In other words, a Linux process can belong to more than one group. So remember from this slide, basically, we have PID, TID, UID, and GID. Okay, that's everything. So in Android, the great idea is that every Android application runs in a separate Linux process. So it has all those attributes I just described. This then gives us the memory separation basically for free. As I said on the previous slide, a Linux process is an area of virtual memory represented on the screen as a box. And within that, we have one or more threads. So in my diagram, I have two Android applications rather at the top. Plus, there's a variable number of Android apps behind all this. And the key thing is then the threads in each Android application can only see their own memory. There is no way that they can access the memory of anyone else's process. So we have memory separation. Application A cannot interfere with the memory of application B. Unless, of course, you really want that to happen, in which case you can do some clever things with shared memory, but I'm not going there. So that brings us then to the file isolation. So this is a little bit more tricky, and we need to delve down into a bit more Linux technicalities. And here I'm talking about something called DAC, Discretionary Access Control. DAC is really just regular Linux or Unix permissions. So just to remember then, the way this works is that every file and directory and socket and whatever else in the file system has an owner, which is a UID, and also a group, which is a GID. And these are the same UIDs and GIDs that we saw just now for processes. And then we have a set of permission flags. So in my example below, I'm doing ls minus l of the root slash, and for no particular reason, I picked up on the bin directory. So just looking at that line then, we have D. So the D indicates what type of thing it is. D is a directory in this case. Then we have the mode, come back to that in a moment. Then we have an owner, which is root, which is user ID 0. And we have a group, which is also root, which is group ID 0. And then finally, at the end of the line, you have the name of the directory. And then we have the mode flags. So we have basically 3 groups of 3 flags. So how do we represent 3 bits efficiently? We use octal. So we have 3 octal digits. This gives me pleasure. When I first started out many, many years ago, everything was in octal. We hadn't invented hex then. So yeah, this is how it used to be. So it's nice to see this lives on. So just looking at the list on the left-hand side there, we have a set of 3 flags which belong to the, or are used by the owner. So let's read the thing on the right-hand side. In order to access a file, the kernel will check the user ID and group ID of the process making the call, and then it will allow the access depending on those flags. So if the user ID of the process and of the file match, we use the first 3 flags. First reading from left to right, actually they're the highest numbers. So that's 100, 200, 400. And we have read, write, and execute for each group. So then we have another bunch of flags for the we have flags for the owner, the group, and the world. Okay, and that's basically it. And that's been the way Unix has been working for the last, whatever it is, 40 years, 50 years, can't remember. So how does that apply to Android? The neat thing here then is that the Android engineers, they decided to use user IDs as basically application IDs. So in Android, every application is a Linux user, which is an interesting way of doing things. So every application has a user ID. The user ID is assigned by Package Manager when you install the app. And, oh yeah, I noticed when I was researching this, in Android 14, they've started calling them app IDs, but really they're UIDs. And there's a range of user IDs that Package Manager can dole out. It starts at 10,000 and goes up to 100,000 minus 1. So yeah, that gives you space for 89,999 apps, which should be enough for everyone. If you're wondering what happens to the first 10,000 user IDs, they are reserved for system use, and they do various special things. So every Android application has a unique user ID, and every application has a private data area, well, actually multiple private data areas. But the main one for internal storage will be /data/data/ package name /files or whatever. And the neat thing about this is that using just the standard Linux DAC mechanisms, we can guarantee that no other application can access those private files. And also, comment at the bottom, since all of this stuff is enforced by Linux, by the kernel, there is no way around it. So sometimes people think that the NDK is magic and it can access all kinds of stuff. Obviously, it can't. Native code has exactly the same restrictions because it's running in the same process ID. Bit of a digression. So in the kind of screenshots that follow, in some cases, I need root access in order to reveal certain things. So I'm actually running a user debug build. And if you're not familiar with these things, when you build the Android platform using ASP, there are three three build types: user debug and user debug and eng. So user is what you normally get. So that's a production build, lockdown, ready for shipping. So that's what you get on your phone. So that's what you normally get in the Android emulator. User debug adds in a whole bunch of debug tools, and crucially, it adds in the su command, so you can type su to get a root shell. And then there's an eng option as well, which isn't so much used these days, but eng is kind of the same as user debug, except that the root shell is the default. And in the slides that follow, you can see which shell I'm using. So a dollar prompt indicates it's a regular shell. A hash prompt indicates it's a root shell. So now we can have a look at some of these files in practice. So this is a little program I've written called file demo. And first of all, I can use the dump sys command to dump the package manager. So dump sys package. And I want it to dump all its package database. So I do dump sys package packages. That will dump out all the information package manager has on all of the applications that have been installed. And this is the section for my little app. So it's com example file demo. And you can see the app ID is 10,089. We can see this in practice if we run the app. So we run the app up by launching it from the launcher. And then we do a PS minus A and N because I want numbers rather than symbolic descriptors. And you can see over here, if we get this right, yeah, you can see the app ID is actually the Linux user ID, which is 10,089. And then just to complete the picture then, if we go look at the private data storage for this application, we should see, yeah, here we are. Let's just do that bit to start with. So this is the owner, the user ID for the app, for the files in the private data area. /data .com.example.filedemo. Okay, it's 1089. And if you look at the modes, well, let's just look at this one down here. The mode is default because this is a directory. And then we have read, write, execute. We have read, write, execute for owner and group, and no read or write for world. So that means that the only Linux processes that can access these files are going to be the ones which have user ID 10,089 or group ID 10,089. And there's only one app in the entire system. There's only one process in the entire system that can do that, and that is my file demo app. Okay, no other app ever is going to be able to access those files. So it's private. So I'm okay to store my banking details in there. No other app is going to be able to steal them. There is a bit of rigmarole here, which I may touch on later on. I'm not quite sure if I'll have time for it. There is, as well as the files, which are just regular files, and there's some other things in there which I'm not going to go into, we also have a couple of directories for cached data. In particular, if you want to just create ephemeral data and you want to cache it somewhere, you do a get cache dir or whatever the function call is, and it will point you to this cache directory. It has a slightly different group ID. Again, for reasons I'm not going to have time to go into. Okay, so that's the basic idea. Applications have user IDs. The user ID controls access to the files I can see. each application can only see the files that have the right user ID, and therefore it can only see its own private data. So this is neat. Supplementary groups. Yeah, okay. I did mention a couple of slides back, you've probably forgotten, that as well as a group ID, a GID, every application has a number of supplementary group IDs. You can see these for real if you want. And I've slightly messed this slide up, but never mind. So here's my file demo. And I'm doing this just because I want the process ID. The reason I messed it up is I noticed the ID here is 116 instead of 87, but just ignore that. So I get the process ID 2071. I can then go into the proc file system, proc 2071, and look at the status. And I want to look at the groups field of status. So you do all that stuff, and these are the supplementary group IDs for my application, 9997, 20116, 50116. What is this all about? Well, again, so 9997 is a special group ID which actually every app belongs to, and it's used for some internal stuff. The one in the 20,000 range, that is to access the cache data, so that's the cache and also the code cache directories. And then there's another one in the 50,000 range, which is there again for basically internal reasons, in actual fact so that profiling works. Okay, so that's the basics of it. What else am I going to talk about? So let's talk about Android users. So we talked really up to this point about Linux users and Linux user IDs. We also have user IDs for Android. Okay, since Jelly Bean, Android has been a multi-user operating system. Woohoo. So how does this work? How do we map Android users onto Linux users? So the answer is Package Manager allocates ranges of user IDs of Linux user IDs, that is, for Android user IDs. And essentially, every Android user gets 100,000 Linux users. And you can work out the user ID based on this little formula here. So the Linux user ID is the Android user ID times 100,000 plus the app ID. For example, so we start with Android user ID 0, which is fine. For reasons that are mysterious to me, IDs 1 to 9 are not used. So the next Android user ID is actually 10. So here's an example then. This screenshot is from my Android device, now running as Android user ID 10, which is actually the second Android user ID. And I'm running the same file demo program, app ID 10,089. So you'll see down here, the user ID is 100,000 plus 10,000 plus 89. And that's a little difficult to read, maybe. It turns out that, oh, I've got this wrong as well. If I miss off the minus n, it actually displays it like this, except it should really be U10 A89, because this was for user 10. This is what comes right in the slides just before you do the presentation. Okay, so we have multiple users. Android users have a range of Linux user IDs, and Package Manager is responsible then for farming those out as you switch users and you run the different apps. Of course, we also need to isolate the users from each other as well as the applications. So this is done through having a separate directory for internal storage for each user and then for each application. So if you go look into /data/user, you'll see there's a subdirectory there for each Android user, in this case 0 and 10. And so when I'm logged on as user 0, my data goes into my files text here. When I'm logged on as user 10, oops, I can't do this, then it goes into this directory. Okay, so again, I can share my tablet typically with other members of my family, and they won't be able to see my banking details because they don't, hopefully, have my login credentials, my fingerprint, or whatever it might be. Oh yes, this. So here we're looking at /data/user/0. Previously I mentioned /data/data. So data user 0 is just a symbolic link, which is put there for backwards compatibility. And then in this bit down here, I do an ls-l. If you look very, very carefully, so this is for user 0. You see the user IDs and group IDs are 10,116. Again, slightly different to before, but never mind. And if I'm user 10, then the user IDs are in the 100 and 10,116. Okay, so everything's good. Now everybody is still firewalled away into separate sandboxes. Okay, so that was how it worked up really until Android 5. Now it turns out that the basic DAC mechanism I just described works pretty well, but it does leave some corner cases. So from Android 5 onwards, more and more of this stuff has been implemented instead in using a separate mechanism called MAC, a mandatory access control. And Linux has several MAC implementations. The one Android uses is called SE Linux. And we've been using SE Linux in Android since Android 5. So now we have both DAC and MAC. Note at the bottom is important. They work together. So you have to pass the DAC tests before you get to the MAC tests. You have to pass both sets of tests. Okay, I could spend literally the whole day talking about SE Linux, and if you want me to, I could do, but maybe not this day. But in 3 or 4 slides, it looks a bit like this. The basic idea of SE Linux is pretty simple. We just label everything, and then we have some rules called policy, which determines which processes can access which files. The complexity comes in the way those rules are expressed and the kind of things you can do with those rules. So we have these things called a context, which is also called a label, and that's of the form user, role, type, sensitivity, and an optional category. Now, the way Android works actually is that the user, the role, and the sensitivity never change. So they are completely uninteresting. The only bit that does change actually is the type. So this is a subset of SE Linux called type enforcement. And you can see the labels typically add a big Z to command line options, and that will show SE Linux labels. So PS minus AZ, we see the labels for processes. And here I've actually chosen 3 Android applications, and we can see they are labeled as being, the first one is a platform app, then we have a priv app and a system app, and the last one is an untrusted app, 25 as it happens. I'll explain all that stuff in a moment. So that's the type of the processes, and then if we look at files with an ls-z, we see that files also have a type. So in this case, we're looking at the cache and the files for my file demo program, and they are all labeled as being an app data file. So in the example I showed then, I showed four different Android applications, and you can see they were labeled as various things. Basically, all Android apps are going to be labeled with one of these four types. There are some exceptions, but these are, that's for a first pass, that's a good way of putting it. So we have untrusted apps. This is any app that is not pre-installed, or any app that is installed by the user is going to be an untrusted app. Then we have platform apps, system apps, and priv apps. These are all pre-installed applications. They are all signed with the platform keys, so they can only be created by the OEM. There is no chance of a third party installing, well, theoretically, there's no chance of a third party installing one of these platform apps. So the SE Linux policy, in other words, the rules, these are coded as part of the AOSP. When you build the platform, you can't change them at runtime. They're encoded in TE files, short for type enforcement. And just to give you a flavor, here is a couple of lines from the TE file for untrusted apps. So just by inspection, you can see we have things like allow. So this is an allow rule. This says this domain, this label can access these resources. So it says allow untrusted app all to be able to access priv app data files, and also they can do some stuff. They have read file permissions and execute permissions for something called an app data file. And an app data file we saw just now was one of these things down here. Okay, so that rule, amongst other things, allows applications to access these directories. Little bit of detail, which possibly is more than we need to go into. Turns out untrusted apps are a little bit tricky because the rules keep on changing from one API level to another. So actually, there are subsets of untrusted app for various API levels. So starting at the top, we have untrusted app. So that applies to API levels or SDK version levels 34 and upwards. And down at the bottom, we have untrusted app 25, which is anything with an SDK version 25 or earlier. And we can see that over the years, the exact nature of these rules has changed from time to time. I'm getting a little bit tight on time, so I'm going to skip a couple of things. Final section then, breaking the rules. Let me say that you can't do this if you are just writing third-party apps, but if you are the platform developer, then you can. So this would apply typically to OEMs, be they OEMs of phones or TVs or vehicles. They need to customize the platform. They need to delve into this stuff. And also, there's a bunch of people who do kind of specialized stuff. So my examples are smart whiteboards, room access booking systems, test and measurement systems, point of sale, advertising. Android is everywhere. Half the things you touch actually are running Android inside. As somebody said just now, the exercise bikes. Your exercise bike is running Android. You have an exercise bike, I assume? I don't actually, but never mind. So we have these kind of lower level things, starting with platform apps. So a platform app is any app that is signed with a platform key. The platform key is the key used for the framework. So it's actually encoded in this thing here. Whoops. This thing here, framework res app, APK. So that's the platform key. If you sign your apps with the same key, you get magic powers. You become a platform app, and you can do a whole bunch of extra things. You just have to trust me on that. There's a further level you can go. You can actually become a system app. So this is a platform app which has the system user ID, UID 1000. Again, this is another magic level. It means that you can access yeah, any files which have the UID and GID system. We have privileged apps. So these are platform apps that are privileged, which means they can be granted privileged permissions. And finally, we have persistent apps. So the persistent flag can apply to any one of the platform apps, but if it's persistent, it means it gets started at boot time, early on, before the launcher gets launched. And not only that, they are restarted if they crash. So they are unkillable. If you kill a persistent app, it just starts up again. So they're very powerful. So these are used for things like the system UI, the phone, and various other low-level bits and pieces. Okay, that is basically everything, and I'm trying to leave a little bit of time for questions. We have a little bit. I just want to do a quick plug for my AOSP meetup. If you're interested in this kind of stuff, and I hope you all are, otherwise you wouldn't be here, just want to let you know that this meetup, the AOSP and the AAOS meetup, it's an online thing. We meet up every 2 months, and we just kind of chew the fat about all these kind of things we've just been talking about. We have a couple of lectures about whatever's interesting at the time. If you're interested, sign up. And you can also go to the main webpage, the one at the bottom here, and you'll see videos and slides of all the talks we've had up till now. It's been going for about 15 months, and I hope it keeps on going for a lot longer.